that's the death of that URL. If you like, if this gets stopped somehow, like you can stop this and start this, no problem. But if this gets stopped, then you've got a dead show.
They said we are live.
Yeah, yeah.
Okay.
The title screen up. You're not.
We should be. We should be in a moment. Give us a moment.
It's got to go to space.
There.
Ooh, a different hold screen.
Hi.
Yeah, Pamela's got all the cool. I gotta learn these tricks.
So hello everyone and welcome to Astronomy Cast, coming to you live from Indian Wells, California. Can I get a woo?
We told you that we were going to go on hiatus and that was all the Astronomy Cast that you got, but that was a terrible lie. You get another episode. Bonus, surprise, you win.
Ninja episode.
And maybe there'll be more. Who can say?
We can't. We're not to be trusted. But we are here as part of the Astro Tours All-Star Star Party you heard us talking about for so many weeks. Well, it happened, and we are here. And I brought clouds.
Well, there was 2 good nights of observing.
Of which I missed one.
Yeah, me too.
And then I bought stuff.
Yeah.
And then Keeper of Maps
Right.
bought things.
Yeah, that's what happens. You buy a telescope, you ruin the skies for all of us. But it's absolutely gorgeous out here. The night sky, the Milky Way, Jupiter, Saturn, and we got a chance to go up to the home of the Virtual Star Party's telescope, thanks to Oceanside Photo and Telescope, and I got to actually give the telescope a hug, which I think. The Rasa telescope that we use for the virtual star parties, yeah, it's a beautiful telescope, and I gave it a hug and I thanked it for all of its kind and helpful work on all of these star parties that we've done. It's amazing to see it in person.
I'm laughing because I hugged a Joshua tree.
That sounds painful.
It kind of was.
Yeah. Don't do that with a cactus.
I did.
Yeah.
I did.
Yeah, but it's beautiful, and I hope this is one of the times we've been doing a bunch of live shows for people, and we've been hanging out around the fire pit in the desert and hanging out until 1 in the morning. Again, this place is like an oven. I don't understand I'm a poor Canadian.
I have enough hair that I have a built-in swamp cooler, so I've been taking my showers after breakfast when it starts to get warm, and I'm good until about 1. If you have enough hair, you have a swamp cooler.
Yeah, I've never experienced anything like this in my life. I am used to a damp forest. Right, used to a nice damp forest where we've got Ewoks running around and we look for Bigfoot. So for me to be in a place where it's not raining all the time is really weird to me, and also the heat and the temperature is mind bending. Yeah, 40 degrees. I didn't even know it went that high. Does the thermometer go past 40? That's not right. Yeah.
And this, sadly, is our last day here, and tomorrow everyone here will scatter to the winds and scatter to the continents across the world. We are an international crew, and it is quite fabulous. And it turns out the way most people got here, well, they relied on the science we're going to talk about in this episode. And we should probably record an episode because we're the only thing between these people, more alcohol, and a banquet.
Okay, all right.
So I am pressing record, and it said F you. Okay, hold on. Audacity has opinions sometimes.
You're going to turn it off, turn it back on again?
Yeah, I am.
So if you're watching this and you weren't able to join us, of course,
You did the mic.
I didn't touch anything.
Yes, you did. You touched the mic. I'm nowhere near that mic.
This is a touchy mic.
It is.
Yeah.
It is.
Yeah. So are you ready to record then?
I think so.
Yeah. Then whatever I said was muted. Don't worry about it.
Okay.
No, go to astrotours.co. Join me in Iceland. We're going to have a lot of fun in January 2020.
Hold on.
Okay, we have better audio now. Sorry, Susie, you're gonna have to cut off like 30 seconds.
Well, no, we haven't started the show
It's
yet.
fixed now. It's fixed.
We haven't actually started the show yet.
It's true.
Yeah.
That's because they're on lag. I just adjusted all the settings.
I have not. I
Settings.
wonder if restarting Audacity did something to the controls on it.
I have no idea.
This
We're better now.
This is not to be trusted.
That is to be trusted through TSA, as Zoom is not.
Oh, really?
Yeah.
I brought my Zoom. I brought my Zoom from Canada. Yeah. Are you kidding?
Fine.
Yeah.
Fine.
Yeah.
Okay.
It's when you bring a blue snowball that they have a problem. Yeah, that's a device that looks like a bomb. All right, let's get started. Astronomy Cast, episode 536, Everyday Relativity. Welcome to Astronomy Cast, your weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser Cain, publisher of Universe Today, and with me, as always, is Dr. Pamela Gay, and I don't have my introduction in front of me, so you're going to have to say your title.
I am Dr. Pamela Gay. I am a senior scientist at the Planetary Science Institute and the director of CosmoQuest. And you should all be mapping boulders at benu.cosmoquest.org.
Stop yelling at them.
I really need them to map boulders and rocks and craters. Please?
So we are recording this episode live from Indian Wells, California, as part of the All-Stars Party Astro Tour. We said that this episode of Astronomy Cast had ended, that we were going on hiatus. That was a lie. This is a bonus surprise. Enjoy. Maybe there'll be more things. Who knows? This is going to be a weird summer. But if you want to, you missed this one, unless you're here and then you listen afterwards. That's weird. But if you want to come on the next trip, I'm going to be going to Iceland in January 2020. So just go to astrotours.co. They're taking reservations now until the middle of July. So if you've ever wanted to go aurora hunting with me, and also glacier hunting, and also like Icelandic troll hunting, you should definitely go to astrotours.co and sign up. We had a great time last time we went, and it was crazy storms. We didn't see a lot of auroras, but I think this time it's really going to work. So astrotours.co and sign up. All right, so relativity is one of the most mind-bending concepts a human can attempt to contemplate. How can different places experience different speeds of time? Well, good news. You're taking advantage of it right now, thanks to the handy gadgets like your phone. Pamela, you wanted to talk about some of the super weird ways that we actually incorporate relativity into our lives every single day. But before we get into some of that, let's just talk about like relativity. What is it?
It is a set of theories most famously worked on by Einstein, worked on actually by a whole bunch of people working together. And it describes literally our place in space and time relative to one another. And it turns out that even though we're so close, I'm not seeing you right now, because it takes the photons of light bouncing off your body a moment to reach me. And as I look out further and further, looking at people in successive rows, I'm seeing them further and further back in time. And as those photons gravitationally interact with things around the universe, their paths get bent and distorted. And that gravity field, well, there's some weird stuff that happens, because no matter who you are, no matter how fast you're going relative to something else, all of us see those photons moving at the exact same velocity.
All right, so let me just understand this for a second. So I'm moving, 100 kilometers an hour. You're moving 10,000 kilometers per hour. Someone is moving just a fraction away from the speed of light, and we're all watching a laser beam that's been shot from the International Space Station, and we're all watching that laser beam, and we are measuring the speed of light of that laser beam as it moves through space at the speed of light, even though we're all moving different distances. And I mean, I guess in our everyday experience, that is not what we experience with say, a bullet being fired. If you're moving close to the speed of light, I'm moving 100 kilometers per hour, we see a bullet moving at vastly different speeds.
And just in more practical terms, when we're going down the highway, we see the cars that we're passing moving relative to us at 10 or 15 miles per hour, unless you're a crazy person. But if you're standing on the side of the road, you see those cars going 60 to 90 miles per hour. And this difference in how we perceive velocities of cars, velocities of runners relative to our own motion is not true with light. No matter who, what you are, light's going 300 kilometers per second, and that's the law.
Right. So, and this, of course, is the amazing discovery that Einstein made, and I'm sure someone could have thought of it earlier, except because it's so weird, right? That time is the thing that changes. It's so hard to wrap your head around, and so fine, this is, and it's not like this hasn't been proven a million times. Einstein's still right. So then what are the practical applications? How do we actually experience this? Are we experiencing time dilation as we're moving around in regular life?
Yes. And where it starts to matter is once upon a time we were worried about whether our pocket watches were closely enough aligned to keep the timetables of the trains in Europe. But nowadays, when we're trying to get a satellite hookup to bring two news stations across the world together, we need to sync up those radio waves so that something that has a millimeter wavelength lines up on the other side of the world. And this requires more accuracy than your pocket watch is going to have.
Yeah.
And as we work out all these timings, we have to take into account the fact that where we are on the surface of the Earth, we're experiencing a whole lot more gravity than the spacecraft those signals are going off of. And this creates one sort of shifting light and shifting time. Those spacecrafts are moving at a different rate around the Earth's center than we are as the Earth rotates. That creates another expansion of time.
Okay, so hold on. Those are two separate issues that maybe we should break up, right? So there's two factors which will impact the amount of time that you experience: gravity wells and velocities. Can you explain that?
So with a gravity well, gravity is going, I shall hold on to you. And the light, as it tries to get away, actually gets redshifted. As you look into a black hole, you see things getting redder and redder as it falls in. And part of this is Doppler shifting, red shifting, but gravity is also playing a role. As you pull out of the gravity well, that pull gets less, and light is getting affected less, time is getting affected less. And so you have a difference due strictly to how far you are from the center of mass and how fast your clock is ticking.
Right, and the practical application of this, if you want a way to sort of think about it, is think about the movie Interstellar, because they gave us this example. Spend some time near a supermassive black hole, spend an hour, and you come back, and it's been 40 years for the people that you left back at home. And so we down here on planet Earth are experiencing less time than people who are out in space.
If they're
not moving. Yeah, they're
yeah.
stationary. Yeah. People who are out in space relative to us, they're not moving, but they're just out there in space. They experience, whoa. So do we see them moving in slow motion? They see us moving in slow motion?
They would see us moving in slow motion, but the catch is you'd fall out of orbit if you tried to do this. It would be very messy. Don't do this.
Right. So just before they plummet to their death, they
Yeah.
notice that we are moving ever so slightly, a little slowly. That's weird, and then the screaming, and then the burning. Yeah.
And the death.
Yeah. Okay. So that's the one half of it, and then the second half of it is the velocity.
And this is that twin paradox that they played with Scott and Mark, the two twin astronauts, where as Scott went round and round the Earth, his velocity, he was accelerated to a higher rate of motion. And you look to see who did the acceleration to figure out whose time was shifted. You look to see who was accelerated. Scott was accelerated. If he wasn't, he would still be on the planet. This experiment wouldn't have worked. He went at the higher velocity, and because he's moving faster, in order for him to see light traveling at the same rate, his clock has to slow down. The way I remember this is he was Buck Rogers in the 21st century, but didn't quite get there because he wasn't going fast enough. Buck's time slowed down, thus
Right.
he made it. So the person who's on orbit, their clock slows down, they visit the future.
So then is there some perfect balance point? Where, because the astronauts are moving at 28,000 kilometers per second. That's way faster than us.
Yes.
So they're experiencing, so we would see them moving in slow motion, but they are outside of our gravity well, and so then they would see us moving in slow motion. So is there some point where they balance out?
Yes, but not with the Earth, because we'd fall out of orbit. If you go to something that has a greater mass, you can find that balancing point where the gravitational redshifting and the time due to your velocity and acceleration, where those two counteract each other. Just not here, do that there. We can't get there yet, so maybe don't do the experiment.
Right. And I know that like when we look out to the other side of the entire universe, the very edge of the observable universe, that is like as far as things can go. And those places have actually experienced 30,000 years of time different to us because they are moving away from each other. Like, time has no meaning.
No, it
Man.
doesn't.
Yeah. All right. So then, I mean, now your head is, you're like, come on, prove it, Fraser and Pamela. Fine, we're going to prove it. What are some of the practical applications, how relativity has moved into our lives every day?
Pokemon.
Pokemon. I got to catch them all.
So
But they're moving in
currently,
slow motion.
We are here when we could be out for the adventure day, and we're both Pokemon Go players.
You're like a serious Pokemon guy. Like, I dabble. And you're hardcore. But fine.
I
So
am.
why could I not play Pokemon Go?
No, well, you could, but it wouldn't know where you are, and you couldn't
You're gonna
catch
grab that.
them all.
You're gonna grab that Pokestop
I'm
right now.
Totally spinning. I got a gift. I will
Oh, that's
send
great. Will you
you a
send it
gift
to me? Okay, great.
Yeah. And Wizards Unite, I play that as well. Nyack, you are a problem in my life. So these things that we do with augmented reality that paint our world with games, with information, that rely on few meter accuracy in our position on the planet. All of these things have to take into account that we're latching on to 3 to 5 satellites high over our heads. And if we weren't latching on to those satellites, we wouldn't have this accuracy. But those satellites are moving. And so we have to do the relativistic corrections to the times, or we would be misplaced in time and space. And all of these things that are fun, informational, and prevent us from getting lost. Google Maps, thank you.
Okay. So then how does that work then? So, your phone knows what time it is, and how does relativity affect your phone?
So we have, you latch on to 3 different satellites, or 3 to 5 satellites to get your position. If it's only 2, you don't know where you are. Your phone, your watch, whatever it is, latches onto 3 different satellites that are all zipping in slightly different directions, all have different light travel times to reach your phone. And your phone listens to the time that the satellite sent the signal, compares the times for the 3 different signals, looks to see where the satellites thought they were when they sent the signal, does a relativistic correction. Using that relativistic correction, it goes, the satellites, when they sent that signal, were actually these 3 places. I now know my separation to 3 different points, and with 3 points, you can figure out where you are in X, Y, and Z, left, right, up, and down. So you're literally drawing 3 measuring sticks between satellites and using relativistic corrections.
Okay, so your phone
Instantaneously.
Right. So your phone detects satellite 1 that's moving towards you and goes, oh, you're moving towards me. So you're moving in slow motion. Therefore, the time that you think you're sending the signal is not the time that I'm actually receiving the signal. I'm going to make an adjustment. But then that other satellite that's over there that's moving perpendicular to me is experiencing a different thing. And also you're out of the gravity well to a certain extent. And it is calculating the velocities of all of these different, and the positions and the directions they're going, and then it is accounting for that. And so if you didn't take Einstein's equations into calculating your position on Earth, would GPS work at all?
No, not really. I mean, it would roughly tell you where you were, but
you're on Earth.
Yeah. and let's not try. We know because of Pokemon Go, relativistic equations make our lives at least more, well, wiggly.
All right. What else? Okay, so fine. So our phone. So like literally for those of us who aren't playing Pokemon Go, those of us who depend on, say, turn-by-turn driving directions, or hiking in the forest, again, you need your GPS to be accurate.
Oh yeah.
So again, like, it's so funny. You have a conversation with someone. It's like, I don't believe Einstein. Like, fine, then throw away your phone. Give me your phone. Actually, doesn't believe in Einstein. I will take your phone, please, and we'll go from there. All right. So what else?
Gold.
Explain how.
This is one of my favorites. So if you've ever looked at the models they have of the lunar landers, there's a whole lot of shiny gold on that stuff. And this is fairly thin, fairly pure, actual gold. And as it's sitting there hanging out going, I'm scattering mostly yellow light, the reason that we see it, the color that we see it, and part of the reason that it makes such a fabulous radioactive particle deterrent is you have this extraordinarily dense atomic core. And this extraordinarily dense atomic core means that the photons that it interacts with, it preferentially shifts their colors as they interact down in the core, and we end up with less UV and blue light than we would if it didn't have this dense core, and thus more yellowy gold than we would without relativity.
But how is it due to relativity?
So one of the awesome things about relativity is it talks about how light gets bent in these high density situations, and you start getting into these effects of, as you get in so close, everything is so dense that the physics goes out of norm. And if you try and use Newtonian physics to describe the motion, Newtonian is like, no, just no, I'm going to misplace those photons and change the color. But with relativity, you can start to figure out how the momentum is changed of the photon, how the wavelength is changed of the photon. You put all of these factors together, and gold, unless it has a lot of impurities, is going to give you a yellow reflection.
But I mean, it's not just gold, right? It's going to be any heavy element pounded into a thin film that has a lot of protons down there in the core, right?
And it's gets even weirder when you start looking at things like Mercury. Mercury flows like a liquid, reflects like a mirror. And the way it's able to do all of this is due to its super high density core again. And so with Mercury again, super high density core, super weird physics, super awesome material. So anytime you broke a thermometer and your teacher didn't catch you fast enough and you played with the mercury, you were playing with relativity. You can say you have experienced it while also experiencing a toxic substance. Don't play with mercury.
Right. But like, I'm trying to imagine how the density of the material impacts the relativity and like the.
So think about a black hole as a high density thing. It changes the physics we work with.
Right, but isn't that from the mass, or is
And
it from the density, or it's the same thing?
Well, it's in many ways the same thing. You can have a star with 10 solar masses of material, but it's not a black hole because the density isn't such that you
Right,
can get
right,
close enough
right.
to the sun. Yeah.
Right. Okay. I see. So it's the density that's actually doing the heavy lifting, as it
Yes.
were. Right.
And there's other places that I have to admit I didn't realize we had to make relativistic corrections until I started doing research to prep for this show. And one of those things that I made in school was an electromagnet. You wrap a whole bunch of wire around your fingers. You use your other hand to attach the wires to the battery. You don't really shock yourself. Some of the electricity goes through your hand. Most of the electricity hopefully goes through the wire. And you can drag things around on the surface of your desk.
With your hand?
Yeah.
Wait. You can. I've never done this. You coil, like I've done this like with a nail.
Yes.
Yeah, you take a nail and you coil a copper wire around the nail, and then you attach the two sides to a battery, and you create an electromagnet. Congratulations, there's your science fair project. Are you saying you can do this with your hand, with your finger?
So you it's just like you're winding up yarn or cables or something. You wrap the wire around your fingers. You have a loop of wire. You pull the loop of wire off your fingers. You don't keep the loop of wire on your fingers. You then grab a battery and you hold the two ends of the wire onto the battery if you're in a cheap school like the one I went to and you don't have battery cases. And then you have an electromagnet. You don't require the nail to make the electromagnet. You require the coils of wire.
So are you like a meat magnet?
Yes. Yes.
Neat.
Now,
A magnet made of meat. All right, please continue.
So
Fine, magnets. We're talking about electromagnets.
we're talking about
I'm
electromagnets.
intrigued.
Now, if you have current running through a wire, moving charge generates a magnetic field. And if you have two wires next to each other that have current, my arms can't do that for the people who are watching. If you have current with flowing in opposite directions in two parallel wires, you can get those wires to attract each other. You can get those wires to repel each other. And to really figure out how much of this is going on, you have to do relativistic equations. Now, when we teach this to freshmen in university, we leave those corrections out because in the grand scheme of all the friction and everything else your standard electrical engineer is going to have to deal with, these are not a problem. But as we get into building faster and faster electronics with more and more delicate wires, a super delicate wire that's getting yanked on by electromagnetism can you can wreck your circuit. So you have to start worrying about these detailed effects.
Right, but that's the force. Like there is definitely a force that is applied to a wire, and same thing. You have a wire, and you apply electricity through the wire, and it goes near a coil, and it'll yank like a magnet. But I don't understand where the relativity of this comes in. Like,
Electrons are moving close to the speed of light.
Right. Okay, so we got something that's moving close to the speed of light, and you've got things that are going in various directions in a computer at close to the speed of light.
Yeah.
And in some cases, moving from one spot to another spot. And when they move really close together, when you're looking at just a couple of nanometers apart, they're interfering with each other and experiencing time dilation and relativity.
And it's in figuring out how strong the magnetic field is that you have to start to look at how fast the charge is moving. Any of us, if we're really bored, can put a natural magnet inside a coil and reverse this experiment and generate electricity by shaking a tube with a magnet in it that goes through the wires. I'm not going to do the hand gesture for that. And And this generates current. Now we're not moving the magnet that fast. The faster we move the magnet, though, the more current is created. The faster the current moves, the more magnetism is created. As we get current flowing faster, you have to take into account relativistic effects.
So would like really advanced, like what modern computers, they're taking that into account.
Yes.
When they're running at whatever clock rate they are, the heartbeat of the computer as it's performing its instructions, it's taking into account the relativistic effects of all of those electrons moving around inside the computer to make sure that as it's sending out instructions and instructions are coming back with the answers, it needs to account for the time dilation for this.
The manufacturers do all of that when
Yes.
they're building it.
Yes, of course.
And then
of course.
it's
yeah,
out
no,
of mind.
you don't specifically have to
My
deal with
processor isn't
Yeah.
worried about that.
Yeah.
And it also becomes a problem when you're dealing with superconductors.
Yeah.
And the faster we get things going, the faster we get our information from point A to point B, the more we have to worry about the corrections we need to make to what happened in the process of getting from point A to point B.
That is amazing.
And just in general, when you're firing an electron around, that electron is like, hi, I'm going fast. Relativity matters.
Right.
And old CRT televisions,
Right.
they were firing electrons at the surface of that cathode. So you have a ray of electrons going
beam,
through
yeah.
a tube to hit a cathode, otherwise known as a cat's electric table, heated table, as near as I can tell.
Right.
Cats liked to sleep on CRTs. Modern cats don't have as much luck, and this is why they claim our keyboards.
Right. But so like an old television, you've got an electron beam.
Yes.
You've got you're one step away from your own Large Hadron Collider there. You've got a particle accelerator in your house firing a beam of electrons in your general direction to entertain you.
Getting stopped by that screen.
But you've got something that's moving at some dramatic percentage of the speed of light, and so you're going to have to take into account relativity.
Especially when you are literally painting the screen with that beam, using the magnets inside to direct the beam to vary the intensity so you see different amounts of light and different colors getting triggered in different places on your screen.
I kind of imagine like the cathode ray tube, a cathode ray emitter is firing out these electrons, but it's accounting for the time dilation that each one of these particles is going to be receiving to make sure that it all comes together for us at exactly the right time. And if it didn't make those kinds of modifications to the timing, television would suck.
Yeah, and it all ended up in how they shaped the magnets was dictated by relativity. So if, like me, you have an old cathode ray television in your basement because the garbage man won't take it and Goodwill won't take it and no one will take it apart and look at the magnets, look at the cathode ray. And the more recent ones aren't as fun as the ones that might be in grandparents' basements or attics. But these were electrons going at 30% the speed of light.
Yeah.
And it matters.
All right. Awesome.
And other than that, we just have to look at things like the sun.
Mm-hmm. Yeah. Well, I mean, we know that the sun is 8 minutes and 20 seconds away or something like that.
Yeah.
So we are seeing the sun as it was 8 minutes ago. That's fine.
But more importantly, if relativity didn't work, nuclear reactions wouldn't work, our sun would not have a power source.
Right.
And
Fusion.
without a star, we'd probably be dead.
Okay, fine. Right. But I will give you that. I appreciate my existence. Thanks, sun. I apologize for all the things I've said about you in the past. But your terrible heat, it's okay. Okay, fine. But like, how does fusion require relativity?
This is the look of where do I start? That required 10 years of university.
Also, you've got 3 minutes.
Yeah, that too. Collisions of particles rely on relativity to dictate how things tunnel from A to B, lower the energy barriers, and allow the things that aren't dictated by quantum mechanics to work. If it's not quantum mechanics, it's relativity that basically describes the sun.
Perfect. I feel like I just got my degree. In your face, education. All right. I think we've reached the end of the time we have here today. So I think the point here that we should really all take away is thanks to Einstein, you were right again. And thanks to relativity, every day our lives are made better by the mind-bending concept of relativity. So
go catch those Pokemon and thank your GPS.
Yeah. One, Nobel Prize winning concept to help you catch Pokemons. Now, did you have any names with you, or should we just generally thank all our patrons? Thank you so much for this bonus episode.
So I don't have any names with me right now to read out. Now, we are going on hiatus. This doesn't mean the work stops. We are going to be working to plan out our next year. Susie is spending the summer going through cleaning up our website, setting everything up. And to thank all of you for kicking around, we're probably going to be sticking lots of bonus randomness into the feed. And we will be returning, as we always do, with Dragon Con and whatever Fraser is doing come September. It's changing for the summer, but we're not going away. And we would not be able to do what we do without all the people who support us on patreon.com/astronomycast. You allow us to pay Susie a living wage for everything that she does.
Thanks, Susie.
Thank you, Susie. And she puts up with so much from the two of us. And thank you. I just kind of don't know what to say.
Yeah, and we'll see you on maybe not till September, or maybe surprise, something else will happen. All right. Thanks, everybody. So you got to press the stop button?
Oh, damn it. Yes.
There you go. Yeah, not the record button again. Did anybody have any questions? This is a live show, so now you get the...
YYZ wants you to explain the Eddington eclipse experiment confirming Einstein's theory, but she would like you to dumb it down.
I can do that.
But, I mean, those are the great discoveries that help confirm relativity, right? I wonder how often that comes into play in our practical day-to-day lives.
Well, just in general, we can pause and explain.
Yeah, no, absolutely, absolutely, yeah.
So for those of you who didn't hear Gordon, Astro YYZ, Astro Wise,
Astro Wise, is that how that works?
No.
But that's what I thought for a long time, and she was amused.
We're doing that. No,
yeah.
that's it. That's it forever. Astro Wise. I love it.
Yeah.
Yeah, okay.
Eddington confirmed relativity observationally for the first time back in the days before super precision timings by traveling to a solar eclipse site and taking glass plate images of stars that were visible near the limb of the sun during an eclipse that normally you couldn't see because their light was getting drowned out by the sun's light. With the moon acting as one of the best coronagraphs you can get, you're able to see those stars. Now, gravity, the closer you get to something with a lot of gravity, the more it's able to bend the path of the sun. Remove the sun, and you're going to see a star over here and a star over here on the sky. Add in the sun, this star stays in the same place as far as you're concerned. This one moves closer because its light is getting moved by the sun's gravity. So what they did with the experiment was, if we have the sun, they looked at the stars, you are now the stars. They looked at the stars when the Earth was right here, and they saw the stars without the sun being in the way. Waited for the Earth to get over here, waited for the moon to get in between, moon blocked out sun, looked at stars, And that light got bent by that intervening sun. So by comparing the positions that were seen with and without the sun acting like a lens to bend the light, we were able to show that the sun bends the light. And that bending of light by gravity, that gravity acting like a distortion lens, that was what Eddington was measuring.
Did you ever see the Eddington and Einstein show? It was like a docudrama.
Yes,
It was like a BBC.
Doctor Who guy, David Tennant.
And I forget who the other one was.
Good Omens guy, go watch it.
Yeah, it was so good, and it totally explained the experiment
And so was Good Omens.
and the difficulty. Yeah, Good Omens. Less science based, more mythology based, but yeah.
I may have had too much coffee.
Yeah.
Getting back to the color of gold relativity, maybe I'm misunderstanding. I think I heard at one point that part of the reason was that because of the density of the gold nucleus, that the electrons inside had to move near the speed of light, that had an effect on the color.
It does. That also has an effect.
Okay.
There are many things that have an effect. Okay, so the question was, or statement was, I had heard that part of the issue with gold acting the way it is because the electrons are so close into the center and they're orbiting so fast that affects the electron levels. That is also part of it. In fact, one of the weird, cool things about gold is because the electrons are all jammed in so close, the differences between the different energy levels is pretty much flat. And this isn't normal for an atom, and all of this is due to the density and the relativity.
Okay.
So yes.
Any other questions about this or anything space related? If you had any questions from the show that we did before as well, we'll be glad to tackle any questions. Yeah, go
Yes.
ahead.
So I'm interested in space mining, and so when you kind of indirectly brought it up in the previous broadcast, you kind of described its purpose for providing a waypoint beyond Earth and as a launch point for further space exploration. But I have a few related questions. How far is, say, space mining away from actually doing it, and what are some of the perhaps Earth benefits? Or like, what kind of, why would we do it? Are there certain special materials that we want to capture, or just more of, consumption for Earth?
Yeah, right. So the question is, why mine space? And the answer is that we want to do space mining because when we go to space, we're going to need stuff to use.
Yeah.
We're going to need metal. We're going to need oxygen. We're going to need hydrogen. We're going to need water. We're going to need rocket fuel. We're going to need uranium. We're going to need gold. We're going to need iridium. We're going to need all these things. And if you have to add a $10,000 per kilogram price tag to get that stuff off of the Earth, it's too expensive to do any of that stuff. So you will be mining from space to support the infrastructure of space. You won't be, you're not going to be necessarily mining an asteroid to then send the gold back home, or mining an asteroid to send the water back home, or drop blocks of iridium back down to Earth so that we can make our electronics. It's all about supporting what we do out in space. And it all depends on us being able to learn how to mine. Because if you set up a robotic factory on some asteroid and it is able to dismantle that asteroid piece by piece and turn it into all these different chemicals and then send them across at very low relative velocities to other places, and they can, manufacturing facilities can turn these into cell phones and solar cells and other robots and more factories and all that. That's how the whole system moves forward. So space mining is all about supporting a space infrastructure.
Now, coming in from the chat, Colin Jones is asking, was Einstein right about space-time being curved? Where does this leave quantum theory given the graviton is unnecessary? This is one of my favorite things that we don't fully know. So there's no proof of the graviton, which is the theorized boson that makes gravity work. Bosons are what moderate force. And so we have virtual photons that carry the electromagnetic force, but we can't detect the graviton. It's theorized to have zero mass, travel at the speed of light, but we also can't yet unify the theories of gravity and the theories of quantum mechanics. So it is possible that gravity is actually the shape of space, the like legit shape of things, and quantum mechanics is describing the interactions between those things, and we don't know, and that is fabulous. I love things that we don't know and open up such weird, awesome things.
I mean, isn't it like if we do find the graviton, then our understanding of physics is wrong?
It's not that our understanding of physics is wrong, it's that we have to say that everything we use to describe space-time is a pretty story, but not an actual physical representation, that the actual physical representation is something the human brain is just like, no.
Yeah, no, I recall, but again, this is not my field until I get my honorary doctorate in astronomy. Which you saw, I just took that class and avoided all of the PhD work right there.
Yeah,
so I'm
exactly,
ready.
exactly.
Diploma, please. All right.
So do we have any thoughts on the questions in the chat?
People are wondering why I'm red.
You're always
I'm always
red.
red. I'm always red by default, but also like you see, I've got
Yeah.
these little booties. Look at this.
So-
Check this out. I don't know if you can see here.
He
I've
has
got like
the-
a line along my.
He's
yeah.
not just a red neck, he's a red ankle.
Yeah.
'Cause he wears sneakers all the time.
Yeah. So no, but we're like where we are in Canada, it is rainy for half of the year, and so the moment the weather turns, we're out nonstop. Yes, I put on sunblock, I turn red, and yet I love it. So we get out into it.
So Raj Luthra is asking, are we going to watch or take part in Asteroid Day in Luxembourg? No, but I'm going to remind you, once again, you should be mapping Bennu.
Yeah, that's the best way to celebrate Asteroid
Yes.
Day is
Go
to
to-
map an asteroid.
Yes, go to bennu.cosmoquest.org. We have 11 days. If all of you out there watching live do 10 images, I think we're done. But all of you have to do this, and I know most of you won't. So everyone grab a buddy and make them do 10 images for the people who don't show up. It's going to take all of us to find the place to do the soil sample, and I'm desperately waiting for the moment that I can send the email to the people who marked the places that we're doing follow-up imaging on and say, hey, you marked a possible site for soil selection. We're going to do follow-up imaging. Thanks. Let me send you that
Yeah.
email.
That's cool.
Please?
So that's really the only way you should celebrate Asteroid Day is to map rocks. You should also celebrate your birthday, mapping rocks on
Anniversary.
Bennu. Anniversaries. It's a wonderful and very romantic anniversary gift. It's just Canada. Yeah, spend your day
Canada
together.
Day, 4th of July.
with friends and family, mapping rocks on Bennu, saving asteroids from a fiery death.
Okay, so we
Got like 5 minutes.
have 5 minutes. I'm trying to figure out DPI 209. You just confused me. We're gonna go with that. So many rocks. I agree.
What's the question?
There is no question. He wrote 1977
Yeah, but
Annie
he
Wilson.
was answering Annie Wilson, Matt Bennu and Will Party.
Oh,
and then
yeah.
it keeps going back. Gravitron. Yeah.
Okay.
Anyway. Does anyone else have a question here in the audience? No. Okay. Then let's wrap things up. Thanks, everyone. I think, what's the plan next? Should we wrap up the live stream? Let's wrap up the live
Let's wrap-
stream so that they don't have to hear about all the fun we're about to have. So thank you, everybody, for watching us live again for this surprise episode of Astronomy Cast. Honor and a pleasure to be here with you. Sorry you couldn't join us here for the All-Stars party, but you should come with me to Iceland, and then we'll do this all again.
And I'm going to try to host Patreon office hours tomorrow off my phone. I will be physically with Keeper of Maps, and so we will try and do what we can. Lord knows what my phone will allow. So we're going to try.
All right.
Thank you all. See you next time.